Hey, and welcome back. My name is MrCaproni, and I teach AP Statistics at Western Hills University High School. We are currently on day 22 of this AP Stats series, and today we're going to be looking at t-tests. Now, we've done a lot with confidence intervals and hypothesis testing so far, but today we're going to be introducing a new type that comes up when a problem arises with our data. So today we're going to take some time and look at that. Now, if you are lost or behind, you don't know what a hypothesis test is or confidence intervals, you can always check out my past videos on YouTube. Just look for MrCaproni, no space, no period, and you'll be able to find all 21 videos that came before this and any videos that we post after this. Again, we're going to be jumping into some new content today, so I hope you learned something new, and thanks for joining me for day 22 of AP Stats. So as I mentioned, we're jumping into chapter 22, which is inference about means, looking at t-testing specifically. So remember, in past chapters, we've looked at a whole bunch of statistics in this section called inference. And inference is where we take information about a sample and we use it to make guesses, predictions, and give us information about the whole population. This is incredibly important in the field of statistics, and it's really the driving force for why we've done everything so far up in this year. We have two major tools of the confidence interval and the hypothesis test. And both of those are grounded in the idea that we know we can't get information about a whole population. It's impossible usually to test every single person in a population. So instead, we have to rely on testing a smaller sample of that population and using that data to make our knowledge, ideas, guesses about the whole population. Then we can base all of our either business findings or decisions in life off of those predictions. So they need to be accurate. Now, when we're looking through here, the reason that we are running into some problems is because in order for us to find a confidence interval or hypothesis test, we really only need two things. We need a properly collected random sample of data. Then after that, we need to compare that with the true population standard deviation. But this is where we run into the issue. If you notice, in a previous video, we covered z-testing and confidence intervals for the z-interval and hypothesis test for the z-test. And I said the number one thing to look for in those questions is the word population standard deviation. And all three of them need to be together. Because here's the reality of the situation. If I'm going out and collecting a sample in order to make a guess about the whole population, more than likely, I'm not going to know the standard deviation of the population. That's what we're collecting the sample for, is to try to make guesses about the population. So the idea that we would already have information on the whole population is extremely rare. So we run into a problem. If I've collected a sample and I don't have that whole population standard deviation, we can't use our z-test, our z-interval, or anything like that. Now, when we were dealing with proportions, this was easy because there are mathematical formulas we've discovered where we can actually find the population standard deviation by doing the square root of p times q divided by n and all of that jazz. But that doesn't work here. It doesn't just transfer over because if we're given the mean and standard deviation of a sample, there's no easy way to jump from that sample standard deviation to the population standard deviation. When people started doing it back in the day, they found that their data was getting a lot of errors, that a lot of their confidence intervals and hypothesis tests were producing false results. And they're like, we can't keep doing this. So they said, hey, why don't we go ahead and try to start doing this by just using the sample standard deviation and making a guess towards the population with that. But the old formulas they used weren't turning out right. The old little sampling distribution curve they were using wasn't giving data that was correct. So what will we do? Like a lot of other great things in life, the answer was finally discovered once a little bit of alcohol was involved. Now, this actually isn't a joke. Guinness Beer Company worker William S. Gossett went ahead and started running into some issues when creating his beer. Now, he was an experimental brewer, which means he basically created a bunch of new beers for Guinness to sell and distribute all across Ireland. Now, just like how the US has the FDA, that kind of helps regulate how food is tested and ran to make sure people aren't getting sick off of it. Ireland had their own rules that they had to follow, and a lot of it was based around the statistical idea of z-tests and things like that. But Mr. Gossett here was like, hey, if I need to do your little Z testing thing, my data that I collect would have to be huge, and I'm going to have to throw out a bunch of beer, and no one likes wasting alcohol. So he decided, hey, we need to come up with a new system where I can still test my alcohol for alcohol content, for taste, for certain levels of other things that go into beer, without wasting all the beer that your little Z distribution requires. So he created something after doing a bunch of studying called the student's T distribution. Now, this is very similar to our normal curve that we get from the sampling distribution. The difference here is that because the sample sizes are sometimes so small, instead of just being one normal curve that we use every single time, it actually ends up being a whole family of normal curves that change based off of your sample size. So when he was looking into this, he said, all right, if I move to this new distribution and do a bunch of curves based off the sample size, which he refers to as the degrees of freedom, then I'll be able to get much more accurate results. I'm not going to run into all the issues I was running in with the Z score stuff, and I'm going to be able to save myself a lot of beer. So what's the difference between this Z and T distribution stuff? So you can actually see two side-by-side curves here. As I told you, the T distribution is actually a whole bunch of curves over and over again. But you can see this one in particular that we're looking at right now is when the sample size was 12. Now, just to let you guys know, when I say the degrees of freedom, when he talks about the degrees of freedom, for whatever reason, instead of just using the sample size of 12 as the degree of freedom, they just do n minus 1, and that gives the degree of freedom. Probably because you wouldn't have a sample size of just 1, so they eliminate that and claim that the first degree of freedom you could have was when the sample size was 2. So we call that the first degree of freedom because you do 2 minus 1, which gives you 1. So in this case, the degree of freedom would be 11. So whenever you see degree of freedom versus your sample size, all you need to do is sample size minus 1. It's nothing fancy. It's nothing special. It's easy peasy. So in this case, it would have a degree of freedom of 11, sample size of 12. So now, again, there is a normal curve for each sample size. And if you were to see all of them stacked on top of each other, essentially, the lower the sample size, the flatter the curve. And as the sample size increases, you start seeing that curve turn more and more into our Z distribution to be like the perfect, like this guy right here. So as your sample size increases, you start seeing something more and more like our little Z distribution here. Okay. Now, once you get in the sample sizes of like 30, 50 or higher, truly it looks almost identical to the Z distribution. But there are a few little tweaks in there that have changed that allows for the data to come out being a bit more accurate because we don't have that population standard deviation. Another thing that is slightly off is because we don't have the population standard deviation and we're relying purely on our sample data, if you got a bad sample, it could end up ruining the whole test. For that reason, your margin of error is quite a bit larger because you're running into purely data off your sample, not off the whole population. So we're just not as accurate in the long run. So you can notice here that this curve is a bit flatter. And a lot of times, if you see pictures of this, the curve will never actually touch the bottom. There's always this little gap down here that doesn't occur with the Z distribution. It's the Z distribution is much, much closer to that line at the bottom, whereas the T distribution is a little bit higher off of it. This accounts for that error. So whereas we say like, hey, you would never see a situation where something's outside of 3 standard deviations. It's just super rare. In this case, you would say it's super rare to be outside of 3 standard deviations, but it's not impossible because this little gap right here means that there would still be some type of probability in our final calculations because there is still an area right there. So the T distribution doesn't have the level of accuracy that a Z distribution does, but that's because we don't have any information about the whole population. All right. So how is this different than the Z distribution? Really, the curve's a little flatter. The curve changes with whatever your sample size is, and it's slightly raised off of the Y or the X-axis there. Now, With that said, there are a bunch of calculations to catch up with what we had already discovered with the z-distribution. At the same time, none of this is going to be surprising. Notice when we were finding z-scores before, we did the sample mean minus the population mean divided by the standard deviation of the population. Well, in a t-distribution, you're going to do the sample mean minus the population mean divided by the standard error or standard deviation of the sample. So really all that changed here is instead of having the population standard deviation right here, or standard error when we're dealing with confidence intervals and hypothesis testing, we're now going to have this sample standard error. And down below down here, instead of dealing with the population standard deviation divided by the square root of n, we're going to have the sample standard deviation divided by the square root of n. So this t-score should look a lot like our z-score. And this standard error of our sample using a sample standard deviation will look very similar to the one we did when we used the population standard deviation. In the long run, what you're starting to see here is that even though we're using a new normal curve, all of the other work behind the scenes ends up being almost identical to what we already know how to do, which is why this isn't going to be any more difficult for you to do confidence intervals and hypothesis testing for. We're going to follow the exact same process we did before, but our calculator is going to use a different curve when it's calculating our end results. So here we have the confidence interval formula. Notice, just like before, we used to look at the mean, but we usually would use it from our sample, plus or minus the z star times the standard error of our population. Notice it's exactly the same. The only difference is they replaced the z star with a t star. They replaced the standard error of the population standard deviation with the standard error of the sample, and the mean pretty much stays the same. And the standard error is only changed because now we use the sample standard deviation in there instead of the population. So this is almost identical. Now, before Z star, we found out that our calculator kind of plugs that in for us and does it all, but we did find a long way of going about doing it by plugging in the inverse norm into our calculator. And we could say like, hey, if we wanted a 95% confidence, then we would just do the inverse norm for the 2.5%, which would be half of the 5% left over, to give us the Z star that would go with it. But guess what? Let's take a look at our calculator on how we could possibly do this with the t-star. So we're going to go ahead and jump over to the calculator. Here we got it. And remember, when we wanted to find z-stars back in the day, what we did is we went to menu, we went to either probability or statistics, and we had to go to the distributions. And we went to this inverse norm. And we said, hey, if I wanted to be 95% accurate on something or 95% confident with our confidence interval, then we would say, okay, that means 5% left over on the outsides, which means 2.5% over here and 2.5% over here. So we put 0.025 for our 2.5%. We left this as 0 and 1. We hit OK. And that told us that our Z star was going to be the 1.96. And we've been saying that over and over that with a 95% confidence interval, we use the 1.96 this whole time and have kind of based all of our things around that. So in terms of a t-star, how would we go about doing that? Well, if you go into your menu, probability, distributions again, notice down here there's also an inverse t, So if I hit that, it's the same thing. If I want to be 95% confident, we put our 0.025 in, and degree of freedom is now something new that we would need to enter. So instead of dealing with just the same curve all the time and getting 1.96 here, this is actually going to change based off of what our sample size is. So let's say our sample size is really small and it's 6. So then my degree of freedom would be 5. And I hit OK. Notice it's going to be a t-star of 2.57. But here's the deal. As our sample size gets larger, you're going to notice that this number will get much, much closer to this number. So for example, if I go in and do the same thing, but this time I go and put in 0.025, and I do a sample size of, let's say, I don't know, a sample size of 41. So my degree of freedom would be 41 minus 1, which is 40. And I hit OK. Notice this is much closer to that original than our last one was. So as this sample size increases, this number is going to get much, much closer to this number. Now, just like before, a lot of times we're not going to have to do this by hand unless they ask for us to do so specifically. So if they ask for a critical value or a T star, Z star, that's where you use this inverse stuff. But for the most part, when we're doing our confidence intervals or our hypothesis testing, we can just go to these two options right here. And notice there is actually the same thing as our Z interval now for the T interval. So when before we did Z interval for our confidence interval, now we can do T. Where we did the two sample Z, now we can do two sample T. So this is going to be very similar to what we've already covered in previous videos. The only difference is we need to identify that we'll be using the T distribution instead of the Z. All right. Now that we know that this is all going to be essentially the same thing we did before, we can pretty much just follow the same process going through. So as always, we got to make sure we can check our assumptions and conditions the same way we would with the Z distributions. So what are the assumptions and conditions here? A lot of them, again, are going to look identical to what we're used to. Number one, the independence assumption is usually checked using the randomization condition and the 10%. We've done this in the past over and over. Remember, we want to make sure that all of our samples and values are independent of each other, so one thing's not affecting another. That's usually done by somewhere in the question it says that it was randomly collected, and then the 10% condition says that the sample itself should not be more than 10% of the whole population, which usually is going to be very easy to do here because a lot of times the T-distribution deals with very small sample sizes. Now, the one that is kind of different than what we've seen in the past is this one, the normal population assumption. Now, they check this using the nearly normal condition, which says that the data comes from a distribution that is unimodal and symmetric. So we check this condition by making a histogram of a normal probability plot. So if I have a list of all of my data from the sample that were drawn, then I just create a histogram of that, and I can kind of see, hey, is it normally distributed or not? Then we can go through kind of these guidelines right here. If the sample size is less than 15, we really only can use this whole process effectively if those samples, that 15 or less sample, has a pretty much normal look to it. In other words, low on the outside, high on the middle. If that's the case, then we're fine and we're good to go. Now, once we get to around a sample size of 15 to 40, then it's okay for that to start looking a little less beautiful in terms of a normal curve. So it says, like, yes, we still want it to be unimodal and it should be reasonably symmetric, but I'm not going to freak out if it's kind of like, maybe a little bit like this. It's not perfect. It's still going to work. The T distribution will still work if that's kind of what it's going to look like here. Once you get above 40, like 30 to 40 range, then it won't matter. You're still able to use this just like we use the Z distributions, where no matter what happens, when we start looking at the sampling distribution from these, it will always end up kind of following like what we did with the central limit theorem that says it turns into being a normal curve once we start looking at it. So whereas we got to be a bit more careful here, in the end, the nearly normal condition is going to be following the same guidelines we had. We just have to be a little bit more careful when the sample size is small. So again, if it's 15 or less, we need it to be almost perfectly normal. If it's 15 to 40, it needs to be close to looking something like a normal curve. If it's above 30 or 40, then we can pretty much say we're solid, we're safe, we don't have to worry about it. So with that said, let's dive into doing some examples and knock this stuff out. So first off, let's look at a confidence interval. I'm not going to read through all this. You're welcome to if you want, but essentially here's what's going on. They're testing salmon from a farm to see if the salmon has things that could be dangerous to people inside of it. If it has a certain level or higher of that, then they're going to deem that we can't use this salmon. So they really need to be careful of the level of what they call contaminants in here. All right. So it says here that what they gave us kind of the information at the bottom down here that the sample size they're using is 150. The mean of that sample size was 0.0913 ppm, which is parts per million. And the standard deviation of the sample was this right here. And it wants us to create a 95% confidence interval about the murex in this salmon. So in other words, we're going to find out on average the whole population of salmon, what is the amount of murex we would expect to be in a fish, a salmon of this group. All right. So how do we go about doing confidence intervals? First off, we would go ahead and check our conditions, which again, I'm going to save for when we do the hypothesis test, just so that we don't have to keep doing that over and over together. But how would we actually find the confidence interval here? Now, we could go by hand and go through all of the different steps of finding this. So that would be find our new standard deviation. We could plug it into either using the table or using technology to find out what our T star is. Notice the degree of freedom here is listed as 149 because we have a sample size of 150. We could plug it all in and do that. Or we could go ahead and just flip over to our calculator, take note of the numbers that we have. Ooh, we're already in the menu over here. And we would go ahead, I'm just going to open up a new one. And menu, statistics. We're going to go to confidence interval. This is a T interval, all right? I know that because there's only one sample, so I don't have to worry about it being two. And we only have the sample standard deviation, not the population standard deviation. If we had the population standard deviation, we could go with Z interval, but we only have the sample, so we're going to go T interval. Now, just like before, we want to switch it to stats because we don't have the raw data, so we'll plug that in. Now it's going to ask for our mean of the sample, standard deviation of the sample, our sample size, and the confidence level we want to find. So let's go ahead and make sure we're not messing any of this up. 0.0913, 0.0913, and the sample size we know is 150. What was that standard deviation over there? We were looking at 0.0495. 0.0495. And it does say we want a 95% confidence, so we're able to leave that there. I hit OK, and boom, just like that, we have our confidence interval. It's beautiful, it's perfect, and I can also copy and paste it. So I'm going to bring this down so we can look at it. So 0.083314 to 0.099286. So what does this mean? It means that we're dealing with means here, not proportions. So if I want to know the true mean of all of my salmon that I got, this sample allows us to say that that true mean level of murex inside of the salmon is probably going to be between 0.08 parts per million and 0.099 parts per million. So we would look at that, we would be able to come up with that we believe the true mean to be somewhere in between those two numbers, which should look very similar to what the final sentence they had. They said, I'm 95% confident that the mean level of murex concentration in farm raised salmon is between the same two numbers or around what we got parts per million. Now notice their numbers are slightly off of ours, just hardly, and the only reason is that we are actually more exact. They pulled their T star from a table, which gave them slightly different answers than ours, and they were rounding throughout their process. So our numbers are actually more exact than theirs are, but on the AP test, they would allow for a certain range above or below what the true answer is, so that either method you use would produce the correct answer. So again, that's looking at the confidence interval for the mean. It's time to move on to hypothesis testing. So let's take a look. Now, some things to be mentioned here is, remember, for hypothesis testing, we do use the formula for z-score a bunch. Don't freak out, because if you check, there's now something called a t-score, and that t-score actually has the same formula as before. The only difference here is that we're going to be using our new standard error formula instead of what we originally were dealing with. And remember, they have to do the n-1 here because this will change depending on what our sample size is. So with that said, let's go ahead and dive into our question here. It's actually going to talk about the same situation with the salmon. We got 150 that we have in our sample. We have a mean of 0.0913 of the murex with a standard deviation in the sample of 0.0495 parts per million. But we find out now that the Environmental Protection Agency's recommended screening value for murex is 0.08, which means if the salmon has a higher than 0.08 level parts per million level of murex, then we have to get rid of that salmon because it's considered dangerous for people to eat. Now notice our mean is higher than this, but remember this is just a sample, not the whole population. So the question is it high enough that we have to reject the whole population, or is that 0.0913 close enough to 0.08 that maybe we just had a bad sample of the fish and we can actually keep it for future use? Now, first thing we would need to do here is check our conditions. Now remember, in order to check if it's independent, we need to make sure it was random and fits the 10%, and then we can talk about the nearly normal after that. Now, looking through here, it says they tested 150 farm-raised salmon. It does not tell us how they did it, which means we are unsure of if this is random or not. And remember, anytime we are unsure of our conditions, what do we say? We are going to proceed with caution. Whoa, and I misspelled proceed. Proceed with caution. So we don't know if this was randomly collected or not. So we're going to say proceed with caution. I know that looks ugly, but you're hearing me, so you know what I'm saying. So we don't have that information. What about the 10%? Do I think 150 is less than 10% of the population? Yes. These salmon farms are not raising just a few salmon. They're raising thousands and thousands of salmon because they're selling them off for all of us to eat and have delicious salmon. So this is going to be well underneath our 10% rule, so we are safe there. In terms of nearly normal, remember, we're really only concerned about this being a problem if our sample size is small. So if we're from 0 to 15, we literally have to plug in the data and check out the graph or histogram if possible. If it's from 15 to like 30 or 40, then we probably should still graph it out and make sure it's at least close to being normal. But once we get above 30 to 40 range, we don't have to worry about it anymore. It's going to follow the same lines as the central limit theorem. It will eventually become normal, so we're fine. 150 is well above the 30 to 40 mark, which means our nearly normal condition is met and we are good to go, which means we can jump on in to writing down the rest of our information, picking our test and all that jazz and doing all of that. Now, we already checked the conditions because we knew which test this was going to be. It even said up there it was a 1 t-test. But remember, the way we know this is because it doesn't give us the population standard deviation. It gave us the sample standard deviation. So I'd mark here that we are using a 1 sample t-test so that the AP reader knows that I know what I'm talking about and which one we're using. Here's my conditions so that we know we went through those. Next off, we need to make sure we're writing out our null and alternative hypotheses. And then we kind of need to record down all of the additional information they give us so that we can plug in our calculator, get our p-value, and move on from there. Now, HO and HA here. What are we actually testing? We're testing to see, is the salmon like content of Murex higher than 0.08? So 0.08 is the number that we're going to be using for our HO and HA, because this is not the number from our sample, it's what we're checking it against. Now remember, we're dealing with means here, not proportions. We want to use an M or a mu symbol instead of the P that we are using for the proportion problems. So again, I'll have that down here. Now, we will end up being able to say that it's beyond their level if it is greater than the 0.08, which means we're actually testing here if it is greater than the 0.08. Now, it doesn't specifically say that anywhere, so you really need to understand the context of this question to get that HA, all right? Now, if it is not able to be proven right there, then it's not saying that the fish is safe, because we obviously see that it might not be. It just means that there's not enough evidence for us to fully commit to the idea that the fish isn't safe. So maybe they would go back and do more samples or things like that, because obviously it's a concern. Or maybe they don't want to throw out their salmon, so they're like, yep, if you can't prove that we're above it, then we're just going to sell it anyway. So we would go ahead and charge forward with this. Now, we still need to write down our information. They did give us an N, which was 150, which means our degree of freedom we'll be using here is 149. They do give us the sample mean, which was the 0.0913, and they gave us the sample standard deviation, which was our 0.0495. Now, what they did not give us is our level of significance, or our alpha. So remember, if we don't have that, the usual default we go with is the 0.05. The other two common ones would be 0.01 or the 0.10 if you want to go on the upper or lower end of that. But since they didn't give us one to go by, we're just going to stick with the 0.05 as our alpha, which means our next step is to go ahead and find our p-value, which means we're going to be jumping over to our calculator to put in this information. Now, We already did the confidence interval over here. Let's go ahead and check what the hypothesis test is going to look like. We'll go to statistics, go down to your stats test. We've already declared this is a t-test for means, all right? We have the stats, not the data. We'll hit OK here. And remember, the MO here, the mu-O, is the number we are using in our null and alternative hypothesis. So in this case, that's our 0.08. The mean is from our actual sample. That's our 0.0913. The standard deviation is also from our sample, which is 0.0495. And our sample size was 150. Now remember, we are going to need to change this because we said that our alternative was that we care that it's greater than that. So we're going to switch that to greater than. We're going to hit OK, and we're going to get our information. Notice our p-value is right here. So we're going to go ahead and copy that and pull it over to our actual screen over here. So let's pull this down into our p-value. And now we get to do the fun part of comparing the two. Is 0.002929 less than 0.05? Yes, it is less than that, which means we get to reject that hoe. So now that we can reject the hoe, that means that we can go ahead and accept the alternative. Now, what was the alternative in this case? It's actually bad news for the company because we can accept that the Murex level average is actually higher than the 0.08 that they're allowed to have, which means in this case, the salmon is going to be contaminated beyond the level that they are going to permit, which means they're going to have to probably throw out this batch of salmon or figure out some other use for it because the levels of Murex is just too high to be safe for consumers. So, end of the day, what happened here? We went through our entire t-test here. It looks very similar to what we're used to. We got a p-value that was less than our alpha, which means at the end of the day, we were able to reject the fact that it was equal to 0.08 and accept that it is indeed more than 0.08, which means the salmon is unsafe for consumption. It's unsafe for us to eat. So we're going to have to reject that batch and move on with some new salmon. Well, thanks for joining me again today, guys. Remember, in this lesson, we went through T-distributions for the first time. This was a new system of normal curves that we can use instead of the Z-distribution when we don't have that population standard deviation to work with. Instead, all we have is the information from our sample. So it changes things up a bit, but in the long run, we were able to tell that it really didn't make much of a difference because a lot of the confidence interval and hypothesis test work that we do, we're able to plug directly into the calculator. And the major difference here comes from the fact that the calculator uses the T normal curves instead of the Z distributions in order to make its final calculations. But our process is almost unchanged, which makes this an easy process for us to continue doing. Remember, if you're feeling lost or confused, or if you want to rewatch this video or see all the videos that came before or after it, you can always find these videos on my YouTube channel at MrCaproni, no space, no period, and you can catch up on any misinformation you have. So again, thanks for joining me today, and as always, guys, stay fit, stay healthy, and have a wonderful day.